Okay, so hopefully, if I write big, you'll be able to see. Okay, so we're going to do a model. Model examples today. Can you see that all right, Fareed? Yeah, okay. And on this board, I'll just make space for some formulae that we'll keep using throughout the session. So we talked last time, we had mass formulae for the sectors on the in the theory, which were minus a half plus the dot product of a sector alpha on the left divided by 8 plus an oscillator contribution. And this oscillator contribution we could also derive as the sum of the different oscillators, like what we call frequency. So we'll get used to using that today. R squared, or actually I was trying to remember to not use left and right last week or in the previous session. So I was using the holomorphic and the anti-holomorphic. So we'll use H and A. Try and remember that. So this as well, use H. Okay, and on the anti-holomorphic side, it was similar, but the vacuum contribution has this 0 point energy of -1, because on the anti-holomorphic side of the heterotic string, you've got bosonic, purely bosonic algebra. So this is the same 0 point energy as you have in just the bosonic string. And then you increase the vacuum energy with the Ramond sector, which is this contribution. So this is like, and you can still read Fareed, even if it's like this. Maybe a bit bigger here. Yes, when you spell it out. Okay, I'll keep trying to write big. And then the oscillator contribution on that side, which again can be written as the sum of the frequencies of anti-holomorphic degrees of freedom. Okay, so we'll use that equation quite a bit. We also have the GSO equation. So the GSO projection. So I'll get rid of it. GSO projection, which was that for sector alpha, we had on one side the spin statistics index, which was plus or minus 1, depending on whether the sector was fermionic or bosonic, which is whether or not the boundary condition of the psi mu, space-time fermions, periodic or antiperiodic. And then these phases, the alpha, and then some basis vector vi. So you in general will project with all of the basis vectors vi on a sector alpha, and that acts on the vacuum of the sector alpha, which is the combination of the Ramond and Dennis vacuum for the fermions in that sector, depending on the boundary conditions. And that is equal to this, the most important part, which is this e to the I pi over 2. And then there's this dot product, which is alpha sorry, vi. How do I write this last time? Vi. I think vi dot f of alpha. I wrote it last time. That's like the bit where the sort of key part of the information is, the projection on the vacuum is. And then that acts on the vacuum of the theory. Okay, so usually when we pick a model, this is fixed, the phases, we choose a set of phases. This is fixed. So the only thing that's varies is this dot product. And then that gives us constraints on the structure of the vacuum for that sector alpha. And then you end up in the Hilbert space with all of the sectors with where these constraints have been implemented. And that's the set of states in your theory. Okay. Okay, any other equations we're going to need? We will also need the ABK rules. The ABK rules for the basis vectors. So because we're using, I'm assuming the fact that we are just using Ramond and Neveu-Schwarz boundary conditions. In other words, real boundary conditions to write these conditions in a simple way. So these dot products are the ones we will be most interested in or need to worry about, and then the ABK rules for the GSO phases, where we write this minus signs VI. So this is the one where we relate the GSO phase between the same basis vector, so the GSO phase between the basis vector and the sector 1, where 1 is always the first basis vector, the one where all of the fermions are Ramond. And then we have VI, VJ. The two different basis vectors are related by EI pi over 2 C VJ over VI. So you can flip. This allows you to like flip the GSO phase, and then
maybe there is a product.
Oh, sorry, yes. So VI dot VI, so this is VI squared, and then this is VI dot VJ. Yeah, so Puri just asked what I've written here. Let me just rewrite this as well. CI over 2 EI dot VJ. Yeah, so this bit period, I was just writing that we always kind of assume that the first basis vector V0 is equal to the purely Ramond vector, which we wrote as 1. Is that right? So it's like V0, just the first basis vector. And then the last GSO. So yeah, the last GSO relationship I'll write up here. So hopefully this one will fit. C VI VJ plus VK. So this is a way of writing a GSO phase where you have a sum. You can decompose. You need the spin statistics operator for the basis vector VI, and then C VI VJ C VI VK. Okay. So we'll use these equations quite a lot. So now let's start on doing a model. So model 1. So the first model we're going to study is the simplest model where the basis, so the basis vectors are simply 1. So we just have one basis vector, which is the purely Ramon basis vector, 1. And so we have to, first of all, we could start by writing the like vector space or the additive group of sectors. So here we have very simple options. We have 1, and we have 1 plus 1. Okay, and 1 plus 1 is where you're just adding where all of each fermion is Ramon, so you're adding them, and that's like where the fermion is basically going around twice, so the minus sign cancels, and you just go back to what we call the NS sector, which is I'll actually write this as 0. So the NS sector is just where, so the 0 sector, also called the NS sector, is where we could write it like this: 0 to the 8. So all of the psi mu's, all the psi mu's are anti-periodic, and all of the gauge fermions, if I was calling phi 1 to 5R1 to 16, complex, which are complex, remember, all of these are also anti-periodic. So that's our full model. We just have to then build the Hilbert space associated to these sectors. These two sectors you can act with oscillators on and build higher and higher mass states, but there's only 2 starting sectors to worry about. So now let's look at these 2 sectors without any oscillators. So you can start off with a pure sector, and then you can gradually add oscillators to it. So let's look at the sector 1. And the sector 1 has, let's try and work out what's the mass on both sides. So m squared h, that sector is -1/2 plus, and then we've got to do this dot product. So alpha dot alpha for the holomorphic side. So remember, the sector 1 is the sector like 1 to the 8, 1 to the 16. So, and they're all complex, so they're all, you count them as 1. So this is 8 over 8. So 8 is the dot product on the left. Just counts the number of periodic fermions on the left. So all of these psi mu's are periodic. And there's no oscillators, so we're saying this is 0, NH. Okay, so that is 1/2. And that means that's greater than 0. So this is a massive sector. even without any oscillators making the mass even higher. It's already massive. So we don't generally care about the massive states. As I said about time, massive states in string theory always generally go with the mass of the string, which is very high, so close to at least the Planck length, the Planck scale. So we generally care about the massless states, m equals 0, and we also will care about tachyonic states, which are where the mass is less than 0. Okay, so the sector 1, which means we don't really care about, so I'll just put, for now, don't care. And then now we look at the NS sector. So the NS sector, the holomorphic mass is -1/2 and then plus 0 over 8, right? Because this dot product, alpha dot alpha is going to be just 0 dot 0, so it's 0. So plus 0. So that is -1/2. So the left moving mass, or the holomorphic mass, is negative, which looks like it could give us tachyons, but also can give us massless states, maybe if we act with an oscillator. So let's do the anti-holomorphic mass. -1 plus 0 is -1. So remember that we also said that we really want level match states. So go right here. If you match the two masses, that's when you have level matching. And that's the same as what we call physical, also called on-shell states, or on-shell states. So we only really care about level match states because the others are unphysical. Yeah, they won't correspond to physical states within the Hilbert space. You just see if Reed is happy yet. Okay. So here, in order to make these level match, we can do two things. So level matching, so I'll just call that level matching. Implies that we need to add half here to make these equal. So we can do N A, so the right, the anti-holomorphic oscillator side, we can add on a half. And that's going to give us a sort of set of states or possible states with -1/2 on both sides. But we could also, so this will give us -1/2, -1/2. So this will actually be tachyons, or a tachyon. A tachyonic. Another possibility is that we could have, so for a massless state, we could increase the mass here by a half and increase the mass here by -1. So to get a massless state, we would have NH equals a half and A equals 1. This is going to give us massless. There's two cases there of interest. And these are going to be the first sort of, these are going to be the only real states in the model, because we've taken all the sectors were 1 and 0. All of the states that result from the sector 1, so whatever oscillators you have, they are all massive. Okay? Because even without oscillators, they're massive. So the only sector we have to worry about is the NS sector. The only possibilities that we care about are when mass is less than or equal to 1. And so the only two level match possibilities are this one, where it's tachyonic, where you have some oscillator only on the anti-holomorphic side, or when you have an oscillator on the holomorphic side and this some oscillators on the anti-holomorphic side as well, where these contributions make it massless. Okay. I'll probably just write this out. Is that okay? Yeah. So we just need to worry about these two cases. Okay, so let's take the first case. So we have the NS sector with NA equals a half. So if you remember when we did the sum, so that's the sum of some right moving frequencies of the fermions is equal to a half. And the frequency was equal to, so anti-holomorphic frequency was 1 minus alpha of some anti-holomorphic fermion over 2. Okay, so we want this to equal a half. So therefore, we can do that with alpha of f bar equals ns 0. So any single ns holomorphic, so anti-holomorphic holo fermion or let me just so does that make sense? That just we want to just pick something with the adds a half, and because we're only dealing with real fermions, we can't, for example, get 2 quarters here. If you had other possibilities here, you might be able to get like a quarter contribution from the frequency, and then maybe you could take 2 oscillators to make a half. But that's not possible because we only have real fermions. GGSO. Okay. Okay. Right. So then we can write what these states look like. Let's say what we're doing is we've got like so this is now I'm just writing the vacuum associated to the NS sector, which is just the case where you've got all of the fermions are anti-periodic, so it's just a load of NS vacuums all together, and then you're acting with some phi bar, because the only anti-holomorphic fermions are phi bar. So this is like phi bar to the A, where A equals 1 to 16. So that's what the state would look like. It's tachyonic. So remember, this is tachyonic. we can actually say that there are 16 possible tachyons here for each choice of phi bar. So 16 choices. We might then wonder, like, well, we haven't talked yet about the GSO projection. So the GGSO projection. You might wonder maybe the GSO projection could like project out the tachyons. Well, the thing is, we only have one phase. So we only have one basis vector, which is 1. So there's only one phase, which is plus or minus 1. And that's a choice. So that's just the choice. But if we try and do the GSO projection, so the only thing we can do a GSO projection with is 1. So remember, when you do this GSO projection, you project the sector with the basis vector vi. We only have the basis vector 1. So the only projection we have really is to do so delta of 0. So we're doing the projection on the sector 0. And then we have the GSO projection of 0 with 1. Acting on the NS vacuum is equal to speed vi pi over 2 of 1 dotted with f of 0 acting on the NS vacuum. But if we look at this side, this the spin statistic of 0 is just going to be plus 1 because it's a bosonic sector. All of the fermion, all the space-time fermion is antiperiodic in the NS sector. This phase, so this phase is equal to C of, so the NS sector is 1 plus 1. And then what you can do is apply the GSO rules to this. So I'll let you do this as like an exercise. So C of 1 plus 1 over 1. You can use this rule here to flip the GSO phase to be 1 over 1 plus 1. And this dot product is going to be 0 because all of the fermions are antiperiodic in the NS sector. So this is the same as C 1, 1, 0, which is the same as writing, just flipping this. Okay. So that's using rule 2. So that's rule 2. And then you can use this rule here where you decompose the sum into 2 parts. And that's going to be delta of 1. So delta of 1 is minus 1 because it's the space-time fermion is periodic. Then you've got D11, D11. Okay. And no matter what you do, that is, so whether if this is plus or minus, this is plus or minus, it doesn't matter. Because these two are multiplied together, they're going to give plus 1. This is just minus 1. This is minus 1. Please. I can't see what I've done wrong, so it must be minus 1. It looks, I don't think I've done anything wrong there, have I? When I flip this, the dot product is 0. Delta. Yeah, this is -1, it must be. Okay, so this side, so I'll rub that out. So what we found there is that this side here, the delta multiplied by the GSO phase, so this side of the GSO projection is all equal to -1. Okay. So in order for this sector to be projected, I'm a bit confused now. I feel like this should be +1. This dot product here, remember the fermion number for an NS fermion is 0, so you just have 0 plus 0 plus 0 plus 0. So this whole thing should be 0. And then this side, you just get e to the 0. So this bit is, this whole thing is equal to +1. Why is this wrong? What's wrong with this GSO phase? Because the tachyons should be in the spectrum. So this side must be +1. So this GSO phase must be +1. But I don't know what I've done wrong. And it's definitely so. So usually this is the kind of thing that happens with the GSO equation that, you know, on here or here you'll get a constraint relating to what this dot product is. But here, because everything is Nebel-Schwarz in the sector 0, then there's no way to there's no constraints, there's no possible way to pick the number of Ramons back here that make this dot product. It's only when this is Ramon that you get something from 0. But there's no Ramon fermions to play with. So this is just fixed. This is dot product fixed at 0, so this whole thing is fixed at -1. Sorry, +1. And then this side is fixed by your choice of the theory. So you either choose this free phase, which is ±1, which fixes this this GSO phase, and then you just compare these two sides. And if the two sides don't match, then the sector, so this sector, would be projected out of the Hilbert space. It wouldn't be in the theory. But if these two are the same, then this would stay in the Hilbert space. And I know that this sector is in the Hilbert space. This projection shouldn't project it out. So I know I've done something wrong. I'm sure actually that this phase, I think, should be +1. But I'm not sure why, from the way I wrote the rules. So I'll just tell you what I'll do next time. But that's, so yeah, so if you just accept the fact that this is actually +1, I think, and this is +1, then we know that the theory should be tachyonic. Because the only GSO projection we have, which is related to this one basis vector, doesn't project it out, or it shouldn't project it out. So this theory that we've wrote down with one basis vector should be tachyonic. Like these these states should give us 16 tachyons. Okay. I'll check why this is wrong. Tell you next time.
In the A 1 to 16.
Yeah.
Not to consider also the penalties.
So we're in 10 dimensions.
Right.
So there's no internal thing. Right. Yeah. Yeah, I'm just I didn't. I'll just remind. We've only been working in 10 dimensions so far. We'll start doing 4 dimensions later. Okay. Right, so that was the tachyonic sector. So the other possibility in our model was the choice, the massless sector. Is more interesting. So the massless sector was where NH was equal to a half. But we also had like a left moving oscillator, and NA is equal to 1. So we have possibly 2 anti-holomorphic oscillators. One thing I haven't mentioned is that you can also have an oscillator from our bosonic operators. If you remember, we also have the x mu, the space-time fermions in theory. So we also have dx mu and dx bar mu. And these the frequency of these. So you can also act for these like these are bosonic creation operators, or it can be bosonic creation operators which have frequency. So the frequency of dx. Well, we'll really just need to worry about this dx bar mu is equal to 1. So it's it kind of reflects the conformal weight. So because you'd expect like a fermion to have conformal weight a half, and you'd expect a bosonic operator to have conformal weight plus 1, or like an integer. So it's very rare that you need to worry about these, because usually to get a massless state, you don't need to add on 1. It's only in this case where you have the vacuum energy of the sector is 0. So you only have the oscillator contribution to nudge it up to a massless state. So this case. So it only really happens, we only have to worry about it usually in the NS sector, or the S sector, which we'll come to later. Okay, so and what's interesting is that these because these are space-time fields, they have space-time representations. The same with psi mu, the space-time fermions. They'll have space-time. They'll form representations under the Lorentz or Poincare group in 10 dimensions. Okay, so here, the holomorphic side, we can use psi mu. Right, so psi mu is the only thing on the holomorphic side, and the frequency of psi mu will be a half. It's fermion. Then on this side, we can either use 2 phi, or we can use this bosonic operator. We can either use 2 fermionic or 1 bosonic operator to make this sector massless. Okay. So I can actually let me just write these a bit more clearly. So, so we get 2 options. So one option is psi mu with 2 fermionic operators acting on the NS vacuum for the space-time fermion and the bosonic anti-holomorphic creation operator. These are like the two choices, 1 and 2. This choice here, so I'll use a different index for that space-time. So this is a 2-index, so it's like a tensor, 2-tensor that forms representations under the Lorentz group. So this the standard thing, doing representations of the Lorentz group, you generally have like the little group. So the little group is like how you choose symmetry, how you form, like you go into the algebra, the Poincare algebra, you have a little group, and then you do this stuff with the highest weight states, and you build but I'm not going to do, maybe later we can do like a group theory session, but this is just like a 2-tensor, and you can, because it's massless, the little group of the 10-dimensional Poincare group is SO8, and a 2-tensor representation of SO8 is like a matrix. So with like U and you could put it into a matrix representation, and the way you usually write it is it decomposes into a symmetric part, an asymmetric part. This is how you decompose matrices into irreducible representation, and a trace. Okay, the symmetric representation will have dimension. So the symmetric part is going to be 8 times 8 minus 1 over 2, I think. And that's going to be related to an object. So we call the symmetric part of this 2-tensor representation, that's called a graviton, or we write it as like G mu nu. So it's like the symmetric tensor related to the symmetric irreducible representation. The asymmetric part is called, I'll just tell you the results. So asymmetric part is called B mu nu. It's also called the Calderon field. And the trace part, so the trace part is just a single number. When you take the trace of the matrix, it's just a number. So the trace part is just relates to a scalar field, which is called phi, which is also called the dilaton. So this is called the Calderon for the anti-symmetric Calderon's anti-symmetric tensor. Okay, so that is the most important states in string theory, because these are like the gravitational. This is also called the gravitational. And the whole point in string theory is that this sector appears in any string theory model. And the way you can see that from this free fermionic formulation is that you will always have an NS sector in a model. So you will always have a sector where you need to have the left and right, the left oscillators to give you mass contribution 1/2, and the right oscillators to give you mass contribution 1. The reason that they are always in the theory is because any GSO projection you can't, there's no GSO projection that will remove these from the theory. Everything is fixed. Like the GSO phase with respect to the NS sector is fixed. So these sectors will always be there. So that was just me talking about this second one. Yeah, so the G mu is the sort of symmetric part which is associated to a graviton, which is the spin-2 field that relates to the so usually we'll just write this as G B phi. So for one, this we notice has one space-time index. So mu. Mu in the light cone gauge, remember, was mu goes from 1 to 8. So in terms of the space-time, it's only like a vector. So it's not a tensor, it's just a one index object. So it's like a vector in space-time. And these choices of A and B, so because these are fermionic, you generally, like, if you swap the order here, then there'll be a minus sign because you have fermionic, they switch. So usually you restrict, I think, to A greater than B. Okay, so these objects, these states actually relate to vectors or vector bosons. And in general, these tell you the gauge group. So they tell you the gauge group of the theory. So they're very important states because of that. In this case, you've got 8. So there's 8 space-time indices. These A and B, remember, are from 1 to 16. In order to calculate, we want to know the dimension of the representation. So this is like the number of possible states here. If you look at all the values of A and B, such that A is greater than B, and you've got the choices for mu, you end up with 496 choices, which relates to the adjoint, which is like the natural matrix representation of the theory. So this is the 496 adjoint of. So because there is these 16 complex fermions, these actually relate to SO. So the spectral orthogonal group of 32 dimensions. So in general, so this is an important rule. So in general, the way you determine the gauge group in a free fermionic model, you can think of it as if you have n complex fermions that have the same boundary conditions in the so with the same boundary conditions the same boundary conditions in all all basis vectors of the theory. So all VI in B, then they give rise, so generates a SO2N gauge group. And that happens precisely because you get states. So these are associated to these kind of states. So sine U, and then A, B. So these gauge boson states, because if you have different basis vectors, different boundary conditions in the basis vectors, these will split into smaller groups. So the A and B's will be restricted basically by the GSO projections, where the boundary conditions are different. So if you have a basis vector where the boundary conditions are different for, let's say, 5R 1 to 4 and the rest of the 5Rs, then the 5R 1 to 4 group will split, and you'll have two components to the gauge group. But so in that case, you might, for example, get SO8 cross SO24 if you had 4 of them split off in terms of the boundary condition groupings from the basis vector. Because of the model we're doing at the moment with just the basis vector 1, these 5Rs, they all have the same boundary conditions. So there's all of them in one group. So you have 16 complex fermions with the same boundary conditions in all the basis vectors, because there's only one basis vector, and that gives you an SO32, which is what I wrote here. But in general, you could have smaller groups where you generate the adjoint of a smaller SO group, and so N in general, you have these gauge bosons will generate the adjoint of SO2N. What do gauge groups factor to at the right side of the board? Which part? Sorry, Fareed, what you asked? Sine mu phi. So that the sine mu phi A phi B is just these gauge bosons which generate the adjoint representation of SO2N, where N is the number of SO2N. I cannot remember this. This bit here. Okay. Yeah, this is just what I wrote here. This is this sector, these states. This is A, B. So in general, these N complex fermions, we're usually thinking of, so in 10 dimensions, we're thinking of them as these gauge fermion side 5R. Okay. Maybe we can go 10 more minutes. So that pretty much completes this model. So this one basis vector model. So in conclusion, what we found was that the model gives you an SO32 gauge group. So let's just summarize what we found. So what we found was that, so summary, the model we chose was B, the basis is just 1, and we said that the only GSO phase that wasn't fixed was this one. And we didn't actually decide whether it was plus or minus one. We didn't really need to. One thing I didn't do in the previous slide or previous board was, one thing you can do is prove that the states I wrote down, the master states from the NS sector, if you do the projection with one, the GSO projection, then it doesn't affect the states. So they are trivially true. So they're trivially satisfied. So maybe I can just, it's very similar to what we wrote before, is we had these two choices, psi mu, phi A, phi D. And psi mu delta x nu. If you do the GSO projection with the basis vector 1, then you get this delta of 0 again of 1, 0 of 0, and then you get e to the I pi over 2. And again, you just have 0 here because that's the fermion number in the NS sector 0. And this is plus 1, and this should be plus 1, although I, for some reason, got minus 1 before. Okay, so let's just, I didn't have that before, but let's just accept it, and you can check that out as well. So the summary, so we have this model, we didn't fix the GSO phase. The key results that we found were that it was tachyonic, which is resulting from these states psi bar A on the vacuum, and we found that it was also, it had SO32 gauge group. So the gauge group is SO32 from these states. And we also found that we had a gravity, the gravitational sector, which had a symmetric tensor, which we associate with the graviton, an anti-symmetric tensor, which is just often called the Karl-Ramon field, and a scalar, which is this dilaton. And it turns out that the number of degrees of freedom, so I wrote this before, the symmetric part of this representation is n times n plus 1 over 2. The number of degrees of freedom here should be equal to 496 as well, for this model. And that's all of the key, that's the main things we care about for this model. Okay, so maybe that's a good place to stop actually. And then, so next week we can then look at models where we add on an extra basis vector and try and get rid of, what we'll do next week is we'll add on a basis vector that removes the tachyon, but preserves these other features of the model, which I mean, this is certainly something good because we have gravity related to this spin 2 field G mu nu. So yeah, that's what we'll look at next week. And we'll also do more practice. In that model, it'll be a bit less trivial doing this GSO projection. What we looked at here was only the NS sector, so there was no Ramon fermions. So the GSO projection was quite trivial. We didn't have to really use this this dot product in the GSO equation. We didn't really have to think about that, so we'll redo that next week, and I'll also explain what I did wrong with the GSO phase. Okay, thank you.